Okay, first I will talk about actually general knowledge about thrust faults, and then give you some examples, especially from Kotvar and some from Suleiman Wedge. And as you know, that thrust faults are basically defined as the faults where the hanging wall block moves upwards against the gravity. That's why they are also called reverse faults. But if the angle of the dip of the fault is smaller than 45 degrees, then they are called thrust faults. And general setting of these faults are basically in convergent settings, but also they are widely exposed, especially in the toes of the deltas, in the continental slopes, and more like slumps and growth faults, that type of setting. Here on the lower left-hand side, you can see a typical, let's say, a folded thrust fault where we in the internal zone or in the hinterland, where the metamorphic rocks, relatively older rocks, are thrusting over relatively younger ones. And then in front of this system, the foreland basins are developed, and the development of this basin is basically because of flexure, as you can see here, and that flexure comes from, in fact, the depressing of the downgoing plate with the load of the advancing overriding plate. Okay, so what are the controls on the thrust belts? And starting from an individual fault to the thrust belt itself. There are various controls on those ones, but I try to actually here simplify them and classify them into 7 categories. Basically, one of the most important control is related to the internal friction angle of the thrust sheets. It is the basic property of the material involved in thrusting, and it cannot be determined, so it has to be indirectly it can be measured. And second important factor is the basal friction, and that controls the thrust belt geometry and the slope, and also it determines the sequence of thrusting, and it is actually changed laterally and in fact in the direction of the tectonic transport direction, results in the change in the development sequence of the thrust faults and their geometries. So it is related to also the critical taper. The critical taper is basically controlled by the type of the material at the Coulomb level, or basically the friction of the Coulomb level, and also if there is any let's say relatively weak material like salt or overpressurized clays and that kind of material, basically incompatible material. And presence of basement highs along the tectonic transport direction, and or also presence of the highs or sediment, variation in the sediment in the direction of the tectonic transport, and naturally also controls the geometry on the plan view and also in the cross section. And another important factor is the rotating indenter. It is not necessary, in fact, to rotate the indenter, but when the two blocks are approaching in an oblique manner, it also creates some kind of rotated indenter effect. So these kind of, in fact, indenters can change the geometry and also the deformation style, not only the actual sequence of events. And the presence of synthetic deposition or erosion, since they change the local stress field, they also change the geometries of the thrust faults and also the sequence of the thrust faults. Okay, when we say sequence, we are referring to the timing of the truss bolts. And basically, there are, in fact, two different types of, let's say, trusting in terms of the material involved. One is the thin skin trusting, which means that everything takes place above at the common level, or we may also call it the sole trust. And basically the lower part is either so plastically deforming or it is completely detached from the basement. The second one is the basement involved. This requires actually a higher energy system. Most of the time, the faults are relatively high angle, which actually requires more energy for the deformation to continue. And most of the actual examples here I'm going to talk about is related to, in fact, thin skin tectonics, which actually requires a basal detachment, and everything is taking place about it. Okay, basically what we think as a trusting is that there is actually a bulldozer. So bulldozer is moving the material in front of it. So like plowing snow or any material during a construction. And what happens most of the time, the truss bolts which are developed close to the plow tend to be older. So here 1, 2, 3 indicates the age of the trusting, so that the age of the truss bolts. So next one will be actually perhaps will be developed somewhere around here. So this is called in-sequence trusting. So you can actually predict the age of the truss bolts with respect to the position of the, let's say, the backstop. That's the backstop here. But depending on the different let's say parameters and the changes along the way, so sometimes some of the faults may develop and they don't follow the order that mentioned above, and they may actually develop out of sequence, so they don't follow. So as you can see here, 1, 2, 4, and then number 3. So this is out of sequence trusting. Here an example, very rough example here. For example, you can see in the Suleiman range, you can see that relatively all the units here, Mesozoic, Cenozoic, and the perhaps the Cretaceous and Upper Cretaceous Paleos. The units are here. You can see the involved rock units are becoming younger from northwest to southeast. This indicates that there is actually a sequence, in-sequence trusting, more or less. I mean, this is a general. But here, these are neogene deposits, and other truss fault is going on here, and it seems that all younger units are trusting over the older ones, and which actually here you can see that taper in the Mesozoic section is basically around 0.5 degrees, and this neogene is almost flat over there, which indicates that actually it is basically telescoped and that's squeezed as edgewise. So then there's almost no the taper here. It's almost horizontal, but trusted over the Mesozoic section, which indicates that this section, because of the age relationship, is out of sequence, because this is younger ones are trusting over the older ones. And if you actually the number of the truss faults, maybe this is the oldest one, and in the sequence this is the youngest one, and this pink one is the youngest of all. So it doesn't follow the same order of events. Okay, so also in terms of actually the involvement of the let's say the style of faulting, basically there are 3 types of faulting, the trusting. Here, the Coulomb type of faulting. This is more like actually intrusion of the salt and clay and that kind of stuff, where the hanging wall block is not included in the trusting. The major shortening takes place in the hanging wall, but the hanging wall responds with folding rather than faulting. And the second one is the fault propagation faulting. So in this case, as the fault propagates, the hanging wall block is actually folded, and in the let's say the older parts are in, they're trusted, but the upper parts are just simply accommodates the deformation with folding. So we don't see any fold on the surface, but we can actually guess that there's folding going on in the deeper part is as blind trust or so. And the third one is the fault manifold. In this case, actually, this is very typical kind of involvement of two different internal friction angles. For example, here the violet part here is has very low internal friction angle, but the overlying units have here higher internal friction angle. That's for that reason we have two different actually geometries. These red lines are the truss wall, but also they are the proportion of the footwall. And you can see how the truss walls are propagating here. This is the largest at number 4, and number 1 is almost as actually trusting as it started yet. So the folding here is associated with the bending of the truss fault or the footwall block, but no truss fault is coming to the surface because the hanging wall block is accommodating deformation simply by folding. Okay, what is actually these things? I'm not going to very details of it here. Is a Coulomb which was actually proposed for the first time by Davis, Sapir, and Dallin in 1983. Basically, according to their idea, the truss wedge, this one, is actually under a very delicate balance. And that balance is first of all controlled by the weight of the truss belt. And here, maybe I should put this one. Okay, this is alpha. This is actually the real critical taper on the surface, and beta here is the angle of truss fault. And here the basal friction of that frictional. Okay, basal frictional. Actually, the shear stress is the function of density of the material, overlying material, acceleration due to gravity, and the height of the truss belt. At each point, it should be actually integrated, and minus the pore water pressure. This is the effective stress times the internal friction angle mu, and actually the theta is the theta is the angle of the truss wedge. So here on the right hand side you can see actually more circle expression of the stress. Here this is internal friction angle. Here phi, this is for the, let's say, competitive material. The red one is for the incompetitive material, or basically the basal friction in the let's say the Coulomb level. So theta and 2 theta, these are the angle between major stress here, this angle, major stress, and the normal to the surface here. So actually the frictional say stress is the function of the normal stress, and this stress, normal stress, can be decreased by actually introduction of pore water pressure at the Coulomb level. This is important because problem in actual controversy in the let's say the faults, because if everything all the truss faults obey this law, then there are cases where we have the very long truss faults and very narrow angles, very shallow angles of the truss faults. So sometimes they are in the range of let's say almost 0 or even negative values. so it doesn't fully explain. But this kind of actually, the Coulomb wedge only explains in the cases of, let's say, normal thrust belts where we have the wedge and the friction at the Coulomb level is relatively high. So here there are some animation. I took this one from YouTube. You can see that this is the thrust angle, and here this is in sequence thrusting. This one is the oldest one, and that one is the youngest one, just to make this one. This one I just actually flipped around it. But it is not actually the full story, and we know now that most of the thrust belts are almost always associated with small normal faults, more or less penetrative every part of the thrusting. So actually, in order to come up with an explanation for the development of these normal faults, is in fact, now we know that here, when the maximum, actually the critical taper is reached, the Coulomb wedge become unstable, and then it actually starts to spread. The propagation of the fault is in fact associated with this spreading. So the thrust belt become in fact relatively low angle, but at the same time, it in fact, propagates. So going up, propagating, going up, and then propagating. During the time of actually this propagation and the decreasing of or spreading of the thrust belt, this extremely small scale normal faults developed on top of the wedge. Okay. So the one of the most important paradoxes actually, there are lots of thrust, especially naps. They are horizontal, and they extend. A single nap extends sometimes tens of kilometers. So which cannot be explained simply by actually pushing from one side and pushing everything the far away. So here is the case. This is, let's say, this is the initial case. This is the friction at the base, and A and B are indicating the points in the initial case. When actually the friction at the base is relatively high, what happens? You can deform only, in fact, the part where the backstop is pushing the belt, and by this way, this deformation may propagate from A to B. But this doesn't explain the naps or overthrust, let's say. But this can be achieved simply by increasing the pore water pressure here. Pore water pressure, actually, one of the most important effect of it is decreasing the effective stress, which means that the Morse circle moves to the left to where, actually, although the material wouldn't be deforming, they can easily be deformed because it in fact decreases the stress, the point-to-point stress in the grains of the rocks, which tend to decrease the normal stress in turn, which decreases the friction between the grains, so that the base of the truss should become almost frictionless. So then it's very easy to move very large masses of rock over the land. And okay. So three different. Sorry, I'm sorry. This should be 3, 2. And this one. Okay. So one of the solution for the paradox or controversy is decrease the basalt friction. The second one, in fact, this is more like a laying carpet below a very heavy table. That's what we do. We don't move whole part of the carpet, but instead we do it in fact in bit by bit. Like this one. This is kind of mechanism here. We are pushing the carpet below the table. And this, as you can see, this actually resembles more to the motion of the salt or diapers, any kind of diapers. So this is associated with salt tectonics. The third one is the gravity gliding, but these are not actually seen everywhere. We can see the gravity gliding, especially in the toes of the deltas, or in the continental, on the Pacific continental margins like Nigeria and the other part, or in offshore Brazil and in the South Atlantic, basically at the where there is very fast deposition, and the material actually coming from the rivers and the deltas, they slowly slide down the slope. And these kind of settings, this is here we have toe thrusts, but in the upper part of the section, the normal poles, they develop, actually they create accumulation space more to the moment of the material downslope. Okay, here you can see actually another type of, let's say, how the basal friction controls the geometry of the truss belt. Here, this is an experiment we did. Actually, Abdul was also there. Here, two different, actually, the basal friction situation. In the high basal friction, what we did, actually, we sprayed glue on the bottom of the sandbox, so that it actually, the sands sticked on it. So then we created a friction equal to the rest of the sand, and which reached around here, the taper is 24 degrees. And the other one, in fact, we didn't do anything at the base, so it was basically a PVC material, which has very low friction. So you can see the difference. Here there are a development of an imbricate fan. So the old faults here are, in fact, developed in sequence. But in the case of basal friction, here with low basal friction, you can see the development of back thrust. And these are the younger ones, and then here the older ones. And so that in the belt, we have relatively, a flat bottom and then sharp. And then again, in fact, we have seen the development of ram flat geometry of the truss bolts, and the low friction is associated with the back thrusts. In the case of, in fact, here the lesson especially in relatively high with the friction is that if the friction is not changing over the length of the truss belt, so in the direction of the tectonic transport, so basically this kind of deformation creates piggyback type of in-sequence thrusting. And also another actual message from the high basal friction is that they don't develop back thrust. In general, the faults are curved. They are not, like in the low friction, they are not planar. And here you can see idealized actually geometry of the stress trajectories. So here this is high basal friction, and this is low basal friction. Okay, when the friction is very low, and in fact the taper is almost zero, and because here this is oil-water emulsion, this is like this is like cream, that people use for their face and that kind of stuff. So in that kind of material, because it almost have no friction at all, so when you apply force from one side of the belt, the stress is actually transferred all the way to the other side, which means that it is actually squeezed from both sides. So this results in development of basically well-developed actually fore and back thrust. In fact, it's very difficult to determine which direction is the tectonic transport, because the taper is almost zero, and also the geometries of the thrusts are identical for each directions. Okay, here you can see actually an example of the low basal friction and decrease of this basal friction in the direction of tectonic transport. This is an animation for the development of the PBX. And this is the north-south cross-section, more or less, from the footwear belt. Here you can see MBT, and also here the main frontal thrust in the salt range. So here that point, more or less, the salt is finished. So the friction has actually become very high. So that actually lead to formation of the salt range thrust. But more will actually follow. This is just an example of what happens when the friction in the direction of the tectonic transport decreases. So progressive increase in the basal friction leads to shorter thrust sheets, increasing taper, and also it creates actually auto thrusting. For that reason, I think that's one of the main reasons why actually active thrusting is going on in the MBT, and also in the frontal thrust in the salt range. So we can have coeval thrusting in both sides simply because of change in the tectonic styles and basically the friction, basal friction. Okay, lateral variation in the friction is one of the best example here. Is actually the distribution of the salt. So the relatively weak material at the base of the thrust belts. So they produce salients, and then the areas with high pressure, they produce recesses. And similar type of geometry may also develop in the case of thicker, where the thicker sediments are there, and where the thinner sediments are there, we can have recess and salient in the thicker ones. This is the same, actually, the example I showed you before. You can see how they are changing. This part, we have longer thrust faults with associated back thrust like this. But in the case of high friction area, there are one-sided, actually, the thrust faults, no back thrust, and the relatively narrow thrust belt, high critical taper, and normally here in this area we would have relatively narrow thrust belts. Here you can see lateral variation. This is actually one of the experiments we did with Dick Newland in 1999 when I was a PhD student in Utrecht. So you can see here the basal friction is decreasing in this from left to right. So you can see how actually thrust belt is changing. Here we have longer thrusts. In the high friction area we have shorter thrust. In this area we have higher taper, and then in this area we have relatively shallower critical taper. And here back thrusts are very common in the low friction area, but as you can see here in the high friction area there are almost no back thrusts. And here we have a typical imbricate fan. Here you can see different combinations they were tried, and here you can see this is low friction. A single thrust bolt can actually accommodate same amount of let's say shortening, and where in the high friction area more than one thrust bolts are developed, so that they have shorter thrust bolts. This is actually just to indicate this relationship: longer thrust bolts and fewer one, and here shorter but numerous thrust bolts. Here the experiment is with changing friction at the basal, basal plane. Here this orange area indicates high friction area. You can see how it is changing. You can see that they are in the single direction, the thrust bolts, but in the low friction area, back thrusts are developing. Same goes with this one. And the change appears as a tear fault or transfer zone in between two different friction area. Same goes with this, oblique convergence type, high friction area, low friction area. The thickness variation is more like actually change in the basal friction. You can see here, and this area, the friction, the sediment thickness are higher, so then actually it creates longer truss holes. So the distance between each successive truss is higher, but in the low, thin, relatively thinner sedimentary areas, we have shorter truss holes. And the setup is here. Actually, there's a step over there, and here the sediments are thinner, over there sediments are thicker. So in the upthrown area, basically, let's say this is a normal fold perpendicular to the direction of the convergence, let's say. So here you can see more folds and less number of, and the long truss folds, more or less what we see in the case of friction variation, but with a difference in since the friction is same in both of them, so then in both cases the back truss are not developed. These are the pictures from top. Stepped indenter is actually no different, just this part starts earlier than that part. When they are approaching, you can see how the geometries are changing. This part is more or less identical to the other part, but here the step appears as a transfer zone between two different areas. But also here, this step area is actually preserved all the way from the start to the actually as the thrusting continues, and that's actually become wider and wider. And in this area, the forward step is actually thrusting here, for example, is over the backward thrust, backward step, so creating a kind of lateral ramp over here. In the case of rotational indenter, here this is an oblique indenter, or more or less it's the same, because when the angle is let's say oblique, so the approaching of this indenter acts like as if it is rotating. You can see here how it is changing. So the number of extra truss holes are increasing in the outer part of the rotation, and they become less and less. But very interesting one is here, because of this rotation, the convergence is also associated with dextral shear in this case. So they create dextral shear, although in fact there is no dextral shear involved in the deformation. You can see here these are the actual marker lines which are put there before the experiment. Basement high, this is more or less like the one in the stepped basement, but with a difference. In the stepped basement, the convergence was parallel to the step. In this case, it's perpendicular to the step. Here, this is the situation. Here, this is without this, a step, and this is with the step. You can see the step is here, and step is there, and there are two different types of materials are used. The orange one is silicone putty, and the white one is the oil-water emulsion. You can see the difference. In the case of silicone putty, you see the truss folds are not developed right at the step, or the normal fold, so to speak. Maybe this one is like, somebody was asking in the previous talk, is the MBT, for example, a normal fold. And here, this is not exactly at the normal fold. But in the oil-water emulsion, which is actually relatively, very low as a strength material, but it mimics more like overpressurized clay. But silicone putty is a viscoelastic material, and which mimics, in fact, salt. So here, in the case of oil-water emulsion, the length of the truss are relatively longer, and the position of the truss fault is not directly at the point of step. In the case of silicon putty, is actually displaced, which means that the truss perhaps develops here and then it's also displaced all the way together. Okay, here it's the two different material. Actually, you can see this is without actually the décollement. There is no, let's say, weak décollement. And these two examples, this is oil-water emulsion and this one is silicone. As you can see here, in the case of no décollement, weak décollement, we can see the forward thrust and numerous back thrust. Actually, they are developing to accommodate the deformation in the forward thrust. Same goes here. In the case of oil-water emulsion, here we can have actually nicely developed forward thrusts and also back thrust and then the secondary forward thrust, same here. But in the case of, you see, the silicone putty, the number of actual back thrusts compared to the oil-water emulsion is less. See, this is simply because, as you can see here, the silicone putty is going through the truss fault. They are intruding itself. So the truss faults are rotating, and this rotates actually. In fact, this rotation results in actually deleting the necessity for the development of back thrust. So since they are thrusting in, they are intruding in, so the back thrust actually few number of back thrust develops. In the case of multiple actually décollement, so this can be simulated by multiple oil-water emulsions here. For example, the white layer over there, you can see that, but also their thickness is very important. I didn't put here to different thickness décollements. Here you can see this is the oil-water emulsion, and then here, basically what we have is multiple actually décollement is not very effective in the case of oil-water emulsion. Basically, you may think that this is all pressurized shale, and there are also all pressurized shale over there, but they are thin. And in that case, the overlying, the upper, say, thinner, the all pressurized shale is not, in fact, affecting overall deformation. But in the case of silicone putty here, the lower part and the upper part, in this case, you can see that here, the lower, actually, the truss faults are completely, the lower and upper part is decoupled almost completely, except few of them, and also here. And you can see that the truss faults are also they're detached parallel. Here, these are they are detached parallel to the bedding, like in this one, completed from each other. So this results in actually extremely complex deformation in the truss faults. In the case of syntectonic sedimentation, because sedimentation or erosion, in the case of sedimentation, you can see here the red sands they are added later as the deformation continues. You can see that the truss faults in the newly added sediments are becoming, in fact, steeper and steeper. This is basically because the local stress field is changed by adding new sands, so they tend to cut up section, and the truss faults become, in fact, steeper as they go in the upper section. And die out, perhaps. Okay, so how about an example? This is actually a study, and from Abdul, it's his PhD study. I will present you actually of the results so far of the 6 actual techniques we used. Those techniques include paleostress inversion, paleomagnetism. I'm not going to involve this one, magnetotherapy, especially for the precise dating of the swan formation, which is in fact is basically recorded in age. AMS, anisotropy of magnetic susceptibility, which is in fact a very good tool for determining strain, basically. And basically, actually, strain measurements are very difficult if they are not, I mean, especially for the mildly deformed sedimentary rocks. In the metamorphic rocks, yes, but not in the sedimentary rocks. But AMS actually has very high potential for this kind of studies. And seismic interpretation, I will actually show you the results of cross-section balancing using the seismic interpretation and surface, in fact, geological measurements. So the study area is here, outlined with dash line, the black line. So I already showed you before. You can see on the right-hand side here the location of the samples. And here the blue ones are the locations of the the sites with the paleostress immersion, and the black ones are the sites for AMS. So we had the chance to actually compare basically the strain and the stress development in the region. So here the results of paleostress analysis. You can see here the blue are the horizontal component of the major stress, and the red are the horizontal component of the minor stress. So some of them here you can see actually that they indicate in this area structural deformation, but if there are no red arrows, it means that they are pure thrusting. And you can also see two different the numbering here, the orange and red ones. Basically, the yellow and red ones, they indicate younger phases, and the green ones are the older phases. And these phases actually are based on the age of the host lithology and also the feed relationships between different types of rocks. Okay, here. The data is extrapolated, and we actually distribute it over the Potwar Plateau using simply by extrapolating the measurements that we have done. In the upper part, you can see the pre-late Pliocene orientations of the major stress, and here you can see the orientation of major stresses in the younger phase, late Pliocene, and almost basically this corresponds to the swan formation and the younger units. You can see actually they're very basic here. These arrows, they indicate how, in fact, the stress field is changing, as if they are flowing into the southwest. And here you see some examples or field examples of these faults and the method used here. And this is the result of these all the measurements and the constructed paleostress orientation, sigma 1, sigma 2, sigma 3, and the quality and the age, so on and so forth, location and number of samples used in analysis, and also number of samples collected in the field. As you can see that the numbers are not matching in some areas. There was spurious data, which means that they were in fact produced. They were not fitting with the analysis. Generally, if the angular deviation of the data is larger than 30 degrees, excluded and then classified as spurious. But it's almost, as far as I remember, less than 4% of pool data, which is common in this kind of settings. The second is the AMS. You can see that in AMS is measured in three directions. So the longer, actually the largest value is more or less parallel to the direction of extension, and the shortest one is K1. Generally, it is associated with compaction of the sediments, so they are useless, but they are actually tells us. If you don't have bedding measurements, they can tell you that they are the poles to the bedding most of the time. And the second or the intermediate value is most of the time associated with, let's say, construction. So here, these are the results. You can see that in also Mian Valley here, for example, they are more or less perpendicular in the northeastern part of the Mian Valley region, but in the western part of the Mian Valley region, they are oblique to the major thrust faults or the stressing faults here. But rest of the area, basically the mean side mean AMS vectors are almost perpendicular to the local structures, the faults, and thrust faults, so on and so forth. On the other side here, this is the extrapolated data. You can see actually changing from here more or less clockwise to counterclockwise directions, as in northeast to northwest south direction. This is very important. It's indicating direction of, let's say, kind of extension or no elongation, and this one here more northeast southwest, here northwest northeast. So there is change somewhere here. Okay, what actually it's also important is the AMS vectors, how they are in vector position. As you can see here, they are basically most of the data is oblate, which means that we have three directions. And in fact, they are more like here, this is not spheroid, oblate, they are oblate, not prolate. So it means that they are compressed, and this axis is basically the compaction of the sediments, and the larger one and the shorter ones are basically the directions of the formation. Okay, this is just to indicate how they have changed. Okay, now the third one, we compare the paleostress orientations with the AMS orientation. So normally AMS, the intermediate, actually the intermediate or the AMS orientation should more or less fit with the major stress, provided that there is actually the amount of strain is low. So we are assuming plane strain, and also we are assuming, let's say, pure shear deformation. Otherwise, in the case of simple shear, there's rotation, so the strain axis and stress axis almost axis never match. What we can see here is more or less the orientation of the AMS data is more or less parallel to the orientation of the sigma 1 in the second phase, with an addition of extra actually orientations here. This is important because that actually it means that we can use K intermediate AMS value as let's say indication of construction. Okay, this is very important. We have actually variation in this side and the western part of the. Okay, what do we have? We also have the, in fact, cross-section balancing from the seismic and surface data. Here, this is the AA, and this is BB, and this is EE. You can see that according to, let's say, the analysis. So there is almost no salt in the north of Mian Valley re-entry and the region. And one of the previous talk that actually said that the amount of construction is more than 100 kilometers, actually, which is around, in fact, the distance from the circular belt to the salt range. So basically, it is the length of this Potvar Plateau, which means that, in fact, the Potvar Plateau is just extended all the way to the south, and is the northern part of the Mian Valley re-entry is just stationary over here. So this is B prime here. You can see that lots of actual salt is involved in the thrusting, and it seems that it's continuous all the way from the MBT all the way down to the frontal thrust. So the precambrian salt over here, and with a step over there. And this is from A prime, from here to there. You can see that, okay, this is BB prime, this is AA prime. Here there's salt, but salt is not actually as abundant compared to the western part of the Potwar Plateau. You can see over here, there are lots of actually here, these salt wells here and there. So it is not actually as plenty as the western one, and which actually results in development of number of, in fact, thrust faults. Although in the western part there is almost no thrust faulting, like in the case of oil-water emulsion, very long thrust fault, and the typical the Coulomb type of folding in the overlying part. But here we have development of thrust faults, fore and back thrusts along the line AA prime. So this is actually our conclusion that okay, in the eastern part the amount of salt is relatively low, and the western part is relatively high. Actually, we came up with this idea based only on the paleostress and AMS results. In fact, I checked the distribution of salt while I was preparing this talk. In fact, it is confirmed. I'm very happy with that one. So in the western area, there is more salt, so that salt is actually the control the deformation over here. That's why there's less number of thrust faults in this area. Basically, there is folding, but I think that folding is related to the the carpet laying type of thrusting in the area. But in the eastern part, the amount of salt is less, which actually resulted in deformation, internal deformation, more than the western part. So this is what I mean. This is more like this one. This is, let's say, Potwar belt. But this situation is important. Here, I think this can explain why we have two different belts in this area, in the western part of the meandering. This is just a, let's say, teaser, but it's actually worth studying. Like this. Okay, when it's reached, so we will have to. In fact, we had kind of actually similar situation in the salt range, but it is more like this. Okay, thanks for listening. I think I did it on time.